Hello everyone, this is a Great Fez and I'm back with my next video on my Ascent Evolution. Um, this one we're going to be talking about the beloved square root function. So to start off, let's go back from the action items and what we did before. I know it's been a while, so I apologize for the delay. So last time we went through and created a gravity turn script, but we didn't, or I didn't like this because it's not very controlled. It's entirely based on the ship's design. I have no way to make sure that the ship is pitching in any direction. In particular, it's just let it go, and that's not very good as far as if there's any changes in wind or anything. That's pretty bad. The other things that we wanted to do is uh, start measuring delta V to see how efficient it is, and this is going to tie into the framework that we're going to be developing to auto tune or tune the parameters based on the ship's design. So I'll get into that later. And then the last thing is just a quick thing, but just to develop a way to switch between like a surface reference frame to the orbital reference frame. And that's just to make the transition between sending following a pitch program to just burning prograde much easier. So first thing I wanted to talk about is just to define what delta V is. It's a very confusing term. It helps a lot um, in orbital mechanics because we deal mostly in changing velocities, right? Usually, whenever you do like a Hohmann transfer, you're just changing how fast you're going at the apoapsis or periapsis, and that goes for pretty much most burns. But so to give you a brief explanation of what exactly it is, in like science terms, I guess, is the amount of speed or velocity that your rocket can change theoretically in space under no other forces. So when the rocket is firing, suppose this is in the middle of the galaxy, there's nothing else around it, there's no atmosphere or anything, and it just fires its rockets. The delta V, uh, which stands for delta velocity, measured in meters per second or feet per second, um, it it'll if you fired your rocket and emptied out your tanks, you'll gain a certain amount of delta V, and that can be calculated here. And this m naught is the mass at the start, and m1 is the mass when you're empty. Um, and then this is the effective exit velocity of the gas, and then you multiply all that to get the delta V. Um, and this will be in terms of meters per second, as I said. So if you had 100 meters per second delta V, and you fired your engine, you would increase your velocity by 100 meters per second. Um, so the other way you can achieve this, which is how I do it in the code, is by integrating the ship's acceleration over time. So if you just calculate the thrust and divide it by the mass, that'll be the acceleration that you would experience under no other forces. And if you integrate that over time, you'll get the total delta V that is being used. And I use this method because as you're going through the atmosphere, the ISP of the engines are changing, and that's the specific impulse, which is a factor that goes into this exit velocity speed value. So if it's changing, that means it's not like a constant value that I can just calculate. Like, so you have to be constantly integrating time. Um, so that next we're going to go into the square root function of how I developed it. I remember a long time ago I saw this picture here to the left of the Saturn V pitch versus altitude plot, and I noticed if you look down here, like the pitch is 90 to 3 degrees, and then based on the altitude, it rolls over. So it's a smooth transition. You can actually graph this and put this into like a function. And for our purposes here, I created a altitude versus pitch, so it's kind of flipped, but it does the same thing. Essentially, what I want to do is make sure that the ship is is pitching over quickly as it's ascending through the atmosphere, and then it levels off here. So if you think about this is totally flat and this is totally vertical at 0, it's going to be pitching over quite quickly because Kerbin's atmosphere is much smaller than Earth's, and we need a lot less delta V to get into space. So we want to be pitching over quickly to get that velocity vector turned and um, to that's pretty much the only reason. But since it's so thin, or the atmosphere is so small, you can start pitching over quite quickly. So this scale factor is something that I'm going to be touching base later, but essentially, um, I calculated this scale factor of 1 is this blue line right here. So that means that if at I want to hit 90 degrees pitch exactly when I leave the atmosphere. That'd be a scale of 1. So the lower the scale, the faster I'm going to hit 90 degrees. So actually, if at the scale of 0.5, I'll be at 90 degrees at 35 kilometers right here. So this is a much quicker pitch over maneuver, um, or a pitch maneuver, I guess, at scale of 0.5 and slower. And what I'll be doing later, just to give you a preview, is I'm going to go through the different chip designs that have different starting thrust to weight ratios and also change the scale factor to show how it's affecting it. And we'll try to develop, or I'll try to go through my methodology there. Thought is. So, um, without further ado, this is the new script that we created. I'll go down and talk about all that's changed. First thing is right here, the pitch program. I changed the inputs from ascent stage or to ascent stage and the switch altitude. The two factors or parameters that you can change are the follow pitch and scale factor. This follow pitch is, as I mentioned before, is how we're going to be switching to following orbital prograde. So if this is false, then we're not going to go through this logic here. And I'll show you that whenever I run the function. The scale factor is exactly what I mentioned before here. It's just changing the curve here to be either sharper or less sharp. And this can go above 1. It's not like I cut it off. For all intents and purposes, I left it between 1 and 0.5. This alt diff is pretty interesting. So if you look at this graph here, oh, the graph starts at close to 0. I think it's actually starting at like 100 or 200 meters, but um, it starts there and goes up. However, if you think about it, if it starts at 0 altitude, well, your ship is actually already, 100 meters up in the air, or like 50 meters up in the air. So the pitch immediately will be non-zero. So with this logic here, this altitude diff here, I've set it so that whenever I actually go into the new stage, the stage 2, I determine what my the ship's altitude is, and then that's going to be my starting point. So it actually goes from this switch alt to 70, or whatever the scale factor is. That's what's going to be determining um, how pitched over I am. And then lastly is just this ascent stage 3, which says if I'm in ascent stage 3, we're going to be following prograde, surface prograde to reduce the what's it called, um, drag, the aerodynamic drag. Um, these scripts here are functions that I've created before. I'm not going to go into super detail because um, they're just to calculate the total delta V that I need. So this one right here calculates how much or puts a maneuver node at the apoapsis to circularize the orbit, and then it prints out how much delta V is needed, and then from there you can add it to the total that's has been used so far, and then that'll give you the total delta V if you were to actually circularize. Which is important because sometimes you'll finish burning earlier, which doesn't mean you use less delta V, you still had to circularize um, at the apoapsis. So I want to make sure I want to see the total use. And I don't actually have any circularization scripts here. I just wanted to throw that in to calculate the total. The actual delta V calculations are here. So the gain is just the acceleration vector, which I get from the sensor. So yeah, the ship sensors that you can put on, like the G meter accelerometer and the actual G meter that calculates gravity, they can actually be pinged by KOS. So if they're on the ship, the ship sensor ACC, which is an accelerometer, and then also G or grav is for gravity, and it outputs a vector. So multiplying it times the throttle will give me the acceleration, or will give me the gain calculation because you only calculate delta V whenever the engine is actually firing. It wouldn't make sense to calculate delta V when it's not because, well, you're not using any fuel, so you're not consuming any delta V or anything. Um, then you calculate that, and then I integrate it over time to get the total delta V. So that's just the basic, how much could I possibly accelerate, and then add that over time. The gain is the actual difference in velocity. The losses is the difference between the two, so it's a negative value. And then efficiency is just a this is just a term that I calculated. I don't think I've ever seen anyone else use this, but it's just how much did you gain versus how much did you use. So the higher this is, the better. Um, let's see. Oh, and then at the very end here, I calculate the delta V, and then I add it to the total, and then I print it out. So let's go ahead and run this. And this is with a ship with a thrust to weight ratio initially of 1.3. The first thing that it does is it waits until the surface is above 30, then it switches into ascent stage and begins pitching. One of the really nice things about this is that there's no sharp transition, right? As soon as it hit 30, it started to go from zero pitch and then increase using that square root function. So it's a nice smooth transition, and it's a continuous one as well. So that's always lovely. You can see here that the gain is increasing. It's measured off of the orbital velocity since that's the one we really ultimately care about. On the ground, you're actually going, I think, 175 meters per second. So if you subtract 175 from here, you'll get the gain. It's You can almost calculate it that way, but I did the dot product just extra accurate. So right now you can see we're our efficiency is really low, but we're slowly increasing it because as we're going up, we're starting to get more. We're starting to point more towards the orbital velocity, which means we're using more of our thrust to accelerate versus turn. And on top of that, the gravity losses, if you've ever heard that term, or gravity drag, is only effective or is only affecting your velocity in when it's pointed in the direction, right? So when you're going vertical, you're losing a lot of thrust, or a lot of delta V to drag or to gravity. But as you accelerate horizontally, you you significantly reduce the amount of gravity drag that you have because gravity is no longer acting, parallel to you; it's acting perpendicular. So here you can see you're getting pretty hot, but I don't think this will actually oh yeah, it does a little bit here. It starts to get a little bit hot, but we are getting out into the very thin atmosphere, so it should be all right. This is one of the things here that I personally don't like to see is after we pass the orbital velocity vector, we continue to pitch down. It's not a very uh, good approach to me, I don't think, because we lose some delta V. But from my actual runs that I've done, the delta V is actually gained whenever we pass it because we're rotating the the velocity vector down a little bit, which means we're getting more of a Hohmann transfer um, trajectory here. So uh, this is going to increase to 150 kilometers, but you can see that it's getting more and more round, which means that we're going to be in a much more efficient trajectory. Because a Hohmann transfer, for those that don't know, is the most efficient way to change your altitude. So if you want to go from 150 kilometers to 300 kilometers, you want to use a Hohmann transfer if you want to save the most fuel. It's definitely the longest way to do it as far as time, but it saves you the most fuel. So now we're just coasting until we get through the atmosphere, and then you can see here we've used a total of 3,224, not 300, sorry. And our efficiency is pretty good. We actually surpassed the 50% mark, so we actually gained more than we lost. Then once this hits 7,000, it runs the calculation. You see it's 160 uh, kilometers or 160 meters per second delta V to put us in a circular orbit here, and the total is going to be 3385. So um, this is this is how I started gathering some data, right? Because right now the scale factor, if you look at this, I'm going to revert since we're done looking at that. The scale factor here is one of those things that I personally don't like, right? It's something that I need to find manually. It's not a calculated variable. Also, this follow pitch, I don't know whether to set it a true or false. Um, it's I want it to be able to do to pick it on its own, I should say, right? So from there, let's go back to here um, and talk about how I collected the data. So pulling up this spreadsheet here. Um, with the spreadsheet, I set the thrust to weight ratio starting on that ship to 1.1. The target orbit is 150 kilometers. And then I went through um, this this spreadsheet. So I said, was there any heat showing? So did I actually see any temperature markers? Was there an explosion? If it was yes, then that's pretty much where it ended. But I set the scale factor to 1. I ran it, find the total delta V, write it down. Then I set the scale factor to 1 again, turned the follow prograde off so that to false here, and then ran it again. You could see that we've saved, roughly 9 delta V here. Um, and then I just continued down the list. So 9, 8, 7, 6, 5, all the way down to 4 were exploded. Stop there. One thing to note here is that at point 5, the apoapsis has actually dropped to 149, so I wouldn't count that as successful, but it didn't explode and it got pretty low delta V, but that's kind of confusing because if the apoapsis was 149, then I still need to use some more delta V to increase it back to 100. Um, but if you notice the trend, the delta V actually goes down the harder that we pull down, the bigger or smaller the scale factor is. So that's a that's pretty interesting to note, right? And from this we can try and find like, hey, where is it going to explode, right? If it explodes here, we kind of want to go step a couple back and set the scale factor to say zero point 0.6, right? Um, or or maybe even 0.7 just to be safe. Then we do the same thing we increase the thrust to weight ratio here, and then we do the same. Here we actually started seeing some heat at zero point 0.6 as opposed to zero point 0.5, and then it exploded at zero point 0.4. One thing to note is, for example, at zero point 0.6, using a lot less fuel, and that's because our thrust to weight ratio is much higher. Gravity drag or gravity losses are very, very big when your thrust to weight ratio is low. The higher the ratio is, the less you lose to gravity losses. And that's just how it is. So here we have just some more data. You guys can take a look. I just gathered it, and then at the end here I kind of put them all like which ones did I pick. So I wanted to At 1.1, I wanted it to be 0.7 because that was probably the um, least likely to explode or anything like that. At zero point 0.6, um, and then zero point 0.5. So now I have this pretty line, right? I didn't mean it to be like a perfect line, but I guess it turned out to be that way. Um, so I can actually auto tune this variable here. I could say, hey, after I determine what my thrust to weight ratio is, calculate the scale factor, and then put it in here so that I don't have to do it again. Um, that way I don't ever have to tune this again. It just auto tune. But this took a very long time. That's part of the reason why it took me so long. I had to run each one of these, and each one took a couple minutes to run, so it's not that quick. I want it to be something more robust, something cleaner, something that I don't have to gather data and run it over and over and over. The other thing I wanted to note is that this follow pitch, um, although it saved me some delta V here. I mean, this one actually was worse. Here it saved me, 4. This one saved me, oh, a great deal. This one here, I think this 74. I might have messed that up. Anyway, um, this one saved me 8. This one saved me 9. Here we have like a savings of 20, 30 roughly. That I don't think is correct. Oh, no, no, it's 330, 20. It'll save me like 30, 30. So, I mean, roughly I get, a savings of max 40, 50 delta V. That's not enough for me to care based on, being 3,000. I mean, 50 divided by 3,000, like less than 1%. Something like that to me is not worth it. I want it to be a much cleaner approach, so I'm gonna leave this value set to true. I want it to follow prograde because it doesn't look pretty to me to, once you're pitching over, now you're going to be pitching back down. So you're actually, inducing some turning losses, but you're gaining some for some abstract reason. It's just, it's just prettier to make it just follow the prograde. So I'll leave it set to true for now. And if you're using this, you could do whatever you want. But I personally am going to leave it there just to for it to be cleaner. I think, and on top of that, I didn't show this, but whenever you do follow the prograde, your angle of attack actually gets pretty low because once you're getting close to that horizontal, your orbital velocity is kind of horizontal. Your surface velocity is also going to be pretty horizontal, so you don't have much of that uh, angle of attack there. And I think that's more of a realistic approach. If we were on Earth with a much larger um, gravity well, with a much bigger atmosphere, you kind of don't want to be pulling any high angles of attack, even though you're very in atmosphere, you're going to be going very, very fast. So lots of heat, lots of potential drag that's going to be induced because of that. So just another added benefit. It just, yeah, part of it's aesthetic, part of it is realisticness, part of it is, um, you know, that's pretty much it. Just those two. um, so going back to here, the next part is critique, and the pitch program. So the pitch program before in the gravity turn was not good. Not that it wasn't pretty or realistic or anything. It's just I don't. I just left it to the whim of the ship, right? So I just turned it on and just let it glide over, and that's not very good. You don't want to just let something go and just hope that it pitches over. You want to set it to something. So we've done that now. We've set it to a smooth function. It's a pretty realistic curve. It's not nothing crazy, no sharp turns or anything. However, it's still very open loop. It's just saying, what altitude are you? You're going to be this pitched over. It doesn't suppose that we had some ship that has a very, high, like the boosters have a lot of thrust, but then all of a sudden they die off, and now we have very low thrust for whatever reason for a long time. This might actually not be able to work because it's not taking into account how the ship's state is. That we have very low thrust, we might need to hold a higher pitch longer. So Um, and of course, the functionality. It took way too long to tune this. That was not fun. I mean, just having it sit there. I could create some. I probably should, but I need to create a system or a script that'll auto run the trajectories for me and save the data. But I just didn't have any personal time, so I had to manually run them. Anyway, we're the next thing that we're going to be doing is creating my most current and I think probably final Ascent script. One of my most proud scripts that I've wrote. To me, I think is really really cool. It uses a system to control the pitch rate. So based on the acceleration of the vertical acceleration and the altitude, it will spit out a rate of pitch so that we will eventually finish off or be pitched over at 90 degrees at a certain altitude. So at this way, I know that no matter what the acceleration is, of how much thrust it has, all that stuff, it's going to take that into account based on how fast it's accelerating and where it already is, and it'll print out a pitch and it'll make it much nicer and smoother and much better controlled. The other thing we're going to do is there's a script out there that calculates the azimuth, or I shouldn't say script, it's more of a function, and it prints out the azimuths that you need to hit a certain inclination. So we're gonna just add that to our script, right? So right now we've just set the heading to 90, so we're going east, just constant, because we're just going equatorial. But now that we're getting close to finishing off, the equatorial thing, we're gonna add a azimuth calculator. I can go over the physics of how that works and the math to help people understand. That's pretty much it for now. Again, if you guys have any comments or questions, leave them below. All the code is put up and I pushed it. So until next time, see you later.